I'm talking about the Ricci-Notation tensor framework for numerical algebraic geometry. Additional details can be found in an archive preprint. The work extends a previous Ricci-Notation tensor framework that I published in 2024. I would like to thank people at the 2024 MathWorks Research Summit with whom I had the privilege of discussing that work informally. I would like to thank them for the useful feedback they gave me, and also in particular Dan Serbu and Adam P. Harrison, who have advised me on the previous work as well as the current work. Algebraic geometry, that's about the solution set or the zero set of a system of polynomial equations. So application areas, they include modular robotics and cryptanalysis. And in the preprint, I talk about additional applications. With linear systems, we use the word rank. So we might talk about a ranked efficient system or a fully ranked system. With polynomial systems, we use terms like zero dimensional, which in that situation, the solutions are only isolated points, or positive dimensional when solutions include lines, surfaces, volumes, etc., which in general are curved. In the preprint, I categorize solution methods into three, two numerical and one symbolic. So the numerical approaches are called continuation and Macaulay CPD, and the symbolic one is called Grosvenor basis. This picture shows me playing tic-tac-toe with a robot at the MathWorks Research Summit in 2024. I actually beat the robot's AI by switching from X's to O's, which confused it, allowed me to play three O's in a row in a column. So the numerical methods for linear systems, they like Gauss elimination and unitary triangular factorization, QR factorization, they triangularize the system. So you get like one equation with one unknown, another equation with two unknowns like that. The approaches to numerical algebraic geometry, they don't do that. On the other hand, you look at the symbolic one, Grosvenor basis, that does create essentially a triangularization like ordering if you want to solve the system. So with the MATLAB symbolic math toolbox, there's the G-basis function. It has an option for what's called a lexicographic monomial ordering, which is basically a creates a triangular system. You can use a Grosvenor basis, you can have symbolic parameters into which you substitute numbers that have numeric round off error, right? That's a hybrid approach. So you could use it like that way for numerical purposes. One nice property about Grosvenor basis and the triangular system is you guarantee zero set invariance. So every solution of the original system is a solution of the triangular system and vice versa. The continuation and Macaulay CPD approaches, they solve for all solutions. They don't create this triangular system. That sounds great in principle, right? But there might be tons of solutions and you might only need one. And with a triangular system, that can help you because maybe that one equation in one variable, right, helps you figure out what is the solution you actually need, like a global optimization approach, essentially. Something else that distinguishes the three approaches in the literature, the Macaulay CPD approach, unlike the others, uses a tensor model and factorization, the canonical polyadic decomposition. So there is a Macaulay matrix, and from that you get a null space, and then you apply this CPD. Now, one thing about this Macaulay CPD approach is it doesn't guarantee zero set invariance. So you get additional zeros initially that have to then some of those extra zeros because they're not in the original system, they have to be invalidated. The CPD literature, although it uses it's a tensor model and factorization, doesn't use the Ricci notation, the notation that tensors best associate with. It's the notation of non-Euclidean geometry, of general relativity, of differential geometry, right? It uses something else. Now, why? It's not necessary. It could be done instead with the Ricci notation. And I have, with my former student, looked at some of that, but I've done other things too by looking at the Ricci notation in the context of tensors for numeric purposes. This was my prior publication in the Journal of Imaging Science and Technology in 2024. With this work, I'm now extending that tensor framework to algebraic geometry, and I'm proposing a generalization of unitary triangular factorization from linear systems, from degree one systems to any degree systems. Okay, so the RT framework, what is that? It's a combination of algebra and software. The software is MATLAB plus a custom toolbox. What I'm doing with this work, I'm extending both parts. So in particular, I'm extending the unitary transforms of linear algebra and linear systems. I'm extending that to tensor algebra and polynomial systems. And I'm doing so with this dual variant index notation, the Ricci notation. I'm also proving with this proposed QR triangularization that there is zero set invariance. So I'm proving that all zeros are preserved and no extra zeros are added. Those are contributions to the extensions to the algebra. I'm also contributing new software. There's a new release of the toolbox. You see the new thumbnail here from my 2026 release. There are new methods for algebraic geometry. There's a sparse multidimensional array class and a MATLAB executable function that accelerates some key sparse operations. Okay, the table here categorizes systems of equations. So along one axis, it's based on the number of variables. So univariate, one variable, multivariate, multiple variables. Generally, the number of equations are proportional to the number of variables. Also, the type of the system of equations, right? Linear equations, but not just nonlinear. Let's consider polynomial as distinct from nonlinear. And in particular, I'm proposing a tensor, Ricci-Notation tensor model for multivariate polynomial systems and a method, the QR, any degree QR factorization. So in this model, there is a vector of unknowns, x. There is a vector of coefficients, a, but the vector of coefficients has indices, j. And you'll notice that the indices j also appear in the model in two places, subscript and superscript, a dual variant index notation, right? I don't want to go into the details of the Ricci notation. That's in another video from my 2024 work. But in this case, I can model a polynomial system. There's also this monomial values function represented by the capital pi. It produces an outer product of the unknown vector with itself multiple times to create a degree d version, all the possible products of the variables d times. Now, the details of the tensor model, they don't matter in the context of this presentation, right? There's the archive preprint. But the point I want to make, some key points, is that the proposed any degree model simplifies in the case of a linear system to exactly the same thing except for the homogeneous formulation, right, as how we model a linear system and also the QR factorization in the case of linear. What changes is now we have to talk about polynomial degree, right? So the original system has a degree, let's call that D. When you triangularize it, in general, the degree could increase. So there's an incremental degree delta D. And then the unitary factors, Q, the linear QR factorization, we have Q and Q star, and we think of them as the same thing, but they're not really. One of them, the Q star, produces the triangular system. The other is part of defining the factorization of the coefficients. In the case of polynomial systems, I realized, it took me some time, realized that I actually there's more differences. So I give them two separate names. One is the forward unitary factor. It produces the triangular system, and the other is the backward unitary factor actually used in defining the factorization of the coefficients. The two unitary factors have to satisfy two identities, same as with the linear case, just it involves tensor notation here. And it simplifies to exactly the same identities for the case of degree one. In this model, I've also introduced a special sparse tensor symbol, the variance sigma symbol. It's a little bit like the Kronecker delta symbol. What it does is you have like x1, x2 is the same as x2, x1 when you talk about polynomials, right? So it deals with those kinds of redundancies. I also have this special zero index vector, which is just the same as the end in MATLAB, the end index value. Apart from the unitary constraints, there's also a triangular constraint, which we can model with the tensor algebra. In the archive preprint, I prove zero set invariance. This doesn't depend on the number of equations and the number of unknowns. That's a factor, but it's not the whole story. So there are two theorems. There's the forward invariance theorem and the backward invariance theorem. The forward invariance theorem proves that every zero of the original system is a zero of the triangular system given the unitary transform using the unitary factor. So in linear algebra, we think of them as the same, unitary factor and unitary transform. But with algebraic geometry, they are distinct. They're related but distinct. So from the forward unitary factor, we can create a forward unitary transform. It involves the unknown variables. And with that, we can prove forward invariance. The backward invariance theorem, same idea. This was harder to prove. It uses the backward unitary factor to create a backward unitary transform and then uses that together with the identities to prove that every zero of the triangular system is a zero of the original system, so no new zeros are introduced. I also propose an algorithm to compute the QR factorization. This computes both the forward and backward unitary factors and the triangular factors. So the algorithm has three parts. The first part and the third part are non-iterative. The first part computes a null space basis that guarantees triangularization, and it also computes initial values for the unitary factors. The last part completes one of the forward unitary factor and computes the triangular factor. The middle part is an iterative part involving optimization. So it minimizes the sum square error over the unitary identities that both have to be satisfied. And it does this with the sum square error and also its analytic gradient derived using the Ricci-Notation tensor algebra. In this work, I'm favoring an outer product model or polynomial systems. In the bottom left, you see a quadratic form. This is one polynomial equation of degree 2. This is a natural way to represent a quadratic form. But behind the scenes, when I use the outer product model, computationally there are disadvantages. So the related QR software that I developed converts from an outer product model, which is helpful for interacting with end users. It converts to a unique monomial model behind the scenes, which reduces the size of the null space basis, and then it converts back again. The unique monomial model, an example of which is shown in the bottom right for a quadratic form, also scales well for high degree systems. So given the total linear dimension, 1 meter, the total surface area, 0.5 meters squared, and the volume, 0.01 meters cubed of a box, you can write a system of three polynomial equations to specify all dimensions. So you can see that in the bottom right corner here. And that system of polynomial equations equals a vector of three zeros. Now, if you have the RT software, the latest release, 2026, you can create a sparse tensor object to define the system. So there's some colors here that show you the relationship between the polynomial model and the coefficients. The software uses classes, and so there is a QR method of the tensor classes that will perform the QR factorization using the proposed algorithm. And this part, at this stage of the work, there's a parameter you have to provide, the incremental degree. If you do that, you'll find that it will calculate a triangularization. I show the polynomial system at the bottom left, resulting from the QR triangularization. The last equation is in one variable only, x3. The second last equation is in variables x2 and x3, and the first equation is in all three variables. So if you take the roots of the last equation, then you find that the numbers are 0.6264, 0.3244, and 0.0492 meters. That actually happens to provide a solution vector because of symmetry. And you can use another method, polyval, to then actually evaluate the original system on this vector, and you'll find that you get approximately 0. Another concept demo. Let's say you have a robot with two segments, each of them 1 foot long. So there are angles that the actuators make with respect to a reference angle. phi 1 and phi 2. Now, if you're trying to direct the end effector, like one end is fixed at the origin, you're trying to direct the other end to a specific point. Instead of formulating the problem over the angles, which leads to a nonlinear system, if you formulate it over four displacements shown here, you get a polynomial system of equations. Two are actually linear equations. The other two equations just establish the fact that, each segment traverses a circle. So if you use the QR method, you'll find that multiple iterations are required. Unlike the box dimensions problem, it actually solves with zero iterations and produces a reduced Grobner basis. This one requires multiple iterations. You can also use this QR method with different numbers of output arguments, and one of them provides additional tensors for identity tests. Now, if you test the identities after just running the QR method with the default settings, it actually doesn't give you high accuracy. You only have three digits after the decimal point for the first unitary identity that's satisfied, and two after the decimal point for the second. That's because the default number of iterations is 400, and based on the current algorithm as proposed, it doesn't fully converge. You could give more iterations, but that's not what's interesting right now, in my view. The algorithm needs to be improved. I stuck with a simple algorithm for now, just a quasi-Newton optimization. Because there were other things I wanted to focus on, some of which are shown here. So if you time how this performed in the two concept demos, and this will depend on the problems themselves and the setting for the maximum number of iterations. In the case of the box dimensions problem, it doesn't make a difference what you set max iterations to, because the initial guess, the first and third parts of the algorithm are enough. In the case of the two-segment arm, it does make a difference when there are more iterations. And then you'll notice that that's the biggest factor in the amount of time that it takes in comparison to the Grosvenor basis, really well-established function in MATLAB Symbolic Math Toolbox that uses a compiled MuPad executable. So with my release of the RTT toolbox, I do have an executable called SPMEX1, and you can compile it in different ways, take out some of the features it provides, and in which case you'll get slower times. So with that two-segment robotic arm problem, if you happen to check the very last equation, you'll find even after 400 iterations, actually even after 0 iterations, it happens to give you the right answers for the solution to the variable x1, which is like related to the first actuator. So it's actually accurate to 15 digits after the decimal point, and that's even with 0 iterations. So that suggests the initial guess is in some ways pretty good, right? It's non-iterative. Now, it's not worth it to look at back substitution at this stage, because there's a lot of non-zeros in the after the factorization in the triangularization. So what happens is, instead, I provide with my toolbox, release 2026, the ARM two-segment concept demo provides a handcrafted solution that is much sparser. So it takes it down from 118 non-zeros to 18 non-zeros, this handcrafted solution. And I can show that it fully satisfies the unitary identities very accurately, and also it triangularizes the system in a way that is equivalent to reduced Grosvenor basis. By the RT toolbox, release 2026, I'm referring to a number of classes and additional functions. The tensor class from release 2024 has new methods for algebraic geometry. There's a new sparse multidimensional array class, sparse1. There's an executable it's a C file that can be compiled into an executable to accelerate key sparse operations. The sparse1 class behind the scenes uses MATLAB's own sparse arrays, mainly 1D arrays, sometimes 2D arrays. And when it uses 2D arrays, it excises unnecessary columns so that the complexity is proportional to the number of non-zeros rather than the number of columns. Unfortunately, if you just use MATLAB's own 2D arrays naively, you'll have dependence on the number of columns. The group of the constructor group of public methods is shown here, as well as the group of unary operations methods are also shown here. Something to note, in the unary operations, two of the methods are starred. So the null method and the RRF method do accelerate with SPMax1 if it's compiled. RREF accelerates directly. Null uses RREF. In RREF, there's a try-catch path. So if SPMax1 or its relevant use case is missing, then it will skip to the catch block. And in the catch block, it will use MATLAB's own RREF function. The binary methods of the sparse one class are shown here, as well as n-ary methods. So in the binary methods, there's a number that are starred. These will accelerate with SPMax1, which has a relevant use case, BSX. The page-wise binary operations, they will produce a sparse two-dimensional array in block diagonal form. And then because MATLAB only has internally sparse 2D arrays and 1D arrays like that, so then it will allow MATLAB's own M times ML divide, MR divide to be used to perform the operation. With the M times and ML divide and MR divide, what I'm doing, including for the page-wise approach, I'm excising all zero rows and columns in coordination to maintain asymptotic complexity proportional to the number of non-zeros and the number of non-zero operations. The n-ary methods, likewise, I'm thinking about asymptotic complexity, making sure it's proportional to, finding a way to make it proportional to the number of non-zeros by using 1D array design. So SPMax1, it uses the CMax API from MATLAB, and it has two main use cases. One is to compute a rank revealing LU factorization, which can be used to produce a row reduced echelon form from which I can get a null space. The other is the binary singleton expansion use case. This generalizes Hartree-Rao products, column-wise Kronecker products, and it proves faster than alternative vectorized approach using MATLAB functions repmat or replm, which are unary singleton expansions. The max function itself, coded in C, I can divide it into three subroutine groups. So SPMax1, its entry point is the subroutine called max function, and then this quickly dispatches to pairs of other main subroutines. So there's a check RRLU, create RRLU, check BSX, create BSX. So the check subroutines do quick checks to see whether it will work based on how I've coded it right now. And if it won't, it will just error. And then in sparse one, the sparse one class will use the catch path. Most of the compute and rearrange subroutines are used by the RRL use case, which is doing a rank revealing LU factorization. That's LU factorization with full pivoting. The rearrange subroutines, they just move memory around quite efficiently. That's easy to do or relatively efficient to do in C using pointers and for loops and mem moves and things like that, mem copies. The compute subroutines, BSX plus and BSX times, they do the broadcasted operations necessary for the BSX use case, staying within the 2D sparse data structure provided by the API. They don't work for infor-nans in operands, but basically sparse one will not call it in that situation. The main contributions of this work, I proposed a unitary triangular factorization for any degree systems. I did this using the Ricci-Notation tensor algebra. And in the process, I generalized unitary transforms from linear algebra to algebraic geometry, including unitary transforms that preserve the geometry of curved space. Preliminary algorithm, it employs a null space basis that is different from how null spaces are used in literature approaches. One of the key aspects of this work is I contributed software release 2026 of the RT toolbox. This has new tensor methods for algebraic geometry, a sparse multidimensional array class with a max function, SPMax1, that accelerates key operations like sparse null space calculation in comparison to MATLAB alternatives, MATLAB own functions to do the same. There are concept demos, box dimensions and arm two segment. They illustrate the developments and also provide some a handcrafted result in the case of the robotic arm example to develop to improve the algorithm further.